In this lecture, let's look at other trigonometric functions. First, let's look at the tangent function. Tangent x, by definition, is the ratio between the sine and the cosine. It equals sine x divided by cosine x. Now, because sine x and cosine x, they are defined for all real numbers x, therefore tangent x is also defined for all real numbers x as long as the cosine x is not 0. Okay, so this is where the function tangent x is not defined. We also have the cotangent x. Cotangent x is the reciprocal of a tangent x. It's cosine x divided by sine x. This is defined to be the cotangent x. So cotangent x is defined again. So cotangent x is defined for all real numbers x as long as the denominator sine x is not 0. So we need sine x is not 0. If we go back to the original setup, which is within a right triangle, say this is the leg A, this is leg B, and this is the angle x. Here's the hypotenuse. Then we see the tangent x equals, well, sine x is A over C, cosine x is B over C. If you take the ratio, the hypotenuse is cancelled. What we left is the opposite leg divided by the adjacent leg. So this is the tangent x within the original right triangle. Similarly, we have cotangent x equals B over A. Now this too can be also be viewed as the original definition of tangent and cotangent, and then we use the connection with sine and cosine to extend it to all real numbers as long as these two functions are well defined. Okay, for example, if I look at tangent pi over 4, which is sine pi over 4 over cosine over 4 with pi over 4, that is 1. And if I look at the tangent pi over 3, this will be the square 3. If we recall the sine pi over 3, well, we say 60 degree over cosine pi over 3. Now if I also, of course, I can define the tangent 0, tangent 0 is 0, right? Because sine 0 is 0 and cosine 0 is 1. Cotangent is just the reciprocal. Okay, if we look at the connection with the coordinate geometry, if I have a line in the coordinate geometry, this is the x, this is y, L is a line on the coordinate plane, say this is angle theta, then the slope of the line is just given by the tangent theta. So tangent theta equals slope of the line L. Okay. Alright, from the definition of tangent and cotangent, we can quickly derive several trigonometric identities. Number 1, we have the tangent x times cotangent x equals 1, right? Because they're just reciprocal to each other. And number 2, I have the tangent pi over 2 minus x, right? We know sine pi over 2 minus x is cosine pi over 2 minus x is sine x. So we just switch the role of sine and cosine, which we get equals cotangent x. It's just cotangent x. Then let's look at the period of tangent and cotangent functions. For sine x and cosine x, we know the least period. Here, when I say period, I mean partial period. The least period is 2 pi. So 2 pi obviously is a period for tangent and cotangent functions, but it's not the least period. The least period is pi. Okay. Let's verify that. So I have tangent x plus pi equals sine x plus pi over cosine x plus pi. Now then we recall, for sine and cosine, if I add pi, so x sine x plus pi equals negative sine x, cosine x plus pi is negative cosine x. So this one equals negative sine x, this is negative cosine x. Well, we have a negative, right? This equals. Okay, now negative cancel with each other. We still get sine x over cosine x, that is tangent x. Okay, so this tells us pi is the period for tangent x, and it's easy to check it is the least period. Alright, similarly we get cotangent x plus pi equals cotangent x. So here the conclusion is pi is the least period for tangent and cotangent. So pi is the least period for tangent x and cotangent x. If we recall the graphs of sine and cosine, we know for sine function within 0 to pi over 2, I would say from 0 to 9 degree, the function is increasing. For cosine x, from 0 to pi over 2, the function is decreasing. Then if you take the ratio of sine over cosine combined together, we see the tangent x is an increasing function. Number 3, we have those vertical lines which is x equals pi over 2 plus k pi. Those are called asymptote. Let's look at pi over 2 and negative pi over 2. When x approaches pi over 2 from the left hand side, that's when sine and cosine, they're both positive. And sine x goes to 1 and the cosine x goes down to 0. If you take the ratio goes to plus infinity, which means it gets larger and larger, it gets aperture larger. Well, if you look at the other direction, it approaches negative pi over 2 from the right? Sine x is it's negative, cosine x is positive. Therefore, it goes to cosine x is positive and cosine x, this one is 0, so this goes to negative infinity. Right? Those are called those vertical lines. X equals pi over 2, x equals negative pi over 2, x equals 3 pi over 2, and such. They are called asymptotes of tangent x. Now let's look at the more properties of the cotangent function. As we said, cotangent function, by definition, the cosine x divided by sine x, it is well defined as long as the denominator sine x is not 0, which is equal to say that x is not equal to k pi, like on the places 0, pi, 2 pi, 3 pi, and negative 3 pi, and those places the function cotangent x is not well defined. It is just the reciprocal of tangent x. So like tangent x, the cotangent x is pi periodic. It's an odd function, and the cotangent pi minus x is negative cotangent x. Also, because we know cosine x is 0 on pi over 2, 3 pi over 2, and negative pi over 2, those places, sine x on those places, sine x is either 1 or negative 1, therefore the cotangent x is 0. Okay, so we have cotangent pi over 2 plus any integer multiple pi, this one equals 0. Okay. Here's the graph of cotangent x. Because it's pi periodic, let's just look at the graph within the typical period from 0 to pi. Like tangent function, it has several similar features. The first one, because the function is odd function, therefore the graph is symmetric. If you look at the whole thing, the graph is symmetric with respect to the origin. And because here we have this cotangent pi minus x is negative cotangent x, the graph is symmetric. If we look at the graph within the period from 0 to pi, the graph is symmetric with respect to x equal to pi over 2. In other words, this branch, if you refract with respect to pi over 2, it coincides with the other branch. Number two, unlike the tangent function, cotangent function within each period is a decreasing function. So this is different from the tangent function. It's decreasing. The reason is because it's just the reciprocal of tangent x, right? If tangent x is increasing, then if you take the reciprocal, that's going to be decreasing, right? Okay, so it's decreasing. Number 3, Like the tangent function, it also has those asymptotes, although the locations are different. The asymptotes is the places when x equals k pi, right? So here is x equals pi, here x equals 0, x equals 2 pi, x equals negative pi. Now within this period, when the function approaches 0, from the right hand side, it goes all the way, right, to the plus infinity. If it approaches, because it's refraction, when it approaches pi, from the left hand side, it tends to negative infinity, right? So we have those vertical lines, they are asymptotes of cotangent x. Next, we want to derive sum and difference formula for tangent and cotangent. Because cotangent is just the reciprocal of tangent, so let's just focus on the tangent. Alright, so our goal is we want to express tangent alpha plus beta in terms of tangent alpha and tangent beta. So that's the sum formula for tangent function. Okay, if we recall the definition, so tangent alpha plus beta is sine alpha plus beta over cosine alpha plus beta. This is by definition. Now for sine and cosine, we have the sum formula. So you can write sine alpha plus beta and cosine alpha plus beta in terms of sine alpha, sine beta, and cosine beta. So this equals sine alpha plus beta. If we recall the formula, this is sine alpha cosine beta plus cosine alpha times sine beta. And cosine alpha plus beta, this is cosine alpha cosine beta and minus sine alpha times sine beta. Now everything is in sine and cosine, but our goal is we want to reduce the formula to be a form that only involves tangent alpha and tangent beta. Therefore, what we do is let's divide on the above and on the bottom. Let's divide the same thing, which is cosine alpha times cosine beta. So we divide cosine alpha, cosine beta on the above and on the bottom. And let's see, what do we get? Okay. So here sine alpha, cosine beta. So cosine beta cancel with cosine beta. Cosine alpha cancel with cosine alpha. So what do we get? First, here what we get is the sine alpha over cosine alpha. That's what we have. And then for this term, cosine alpha cancel with cosine alpha. So sine beta, cosine beta. So that's sine beta over cosine beta. Now this one divided by cosine alpha, cosine beta, just go away, it's just 1. And here left is sine alpha, there's nothing to cancel. So sine alpha, sine beta, cosine beta. Okay, we have sine alpha over cosine alpha, sine beta over cosine beta, or cosine beta. Okay, now the point is, okay, this by definition is just tangent alpha, and this one by definition is just tangent beta. Okay, similarly, so this one is tangent alpha, and this is tangent beta. Therefore, if you replace by tangent alpha and tangent beta, eventually we derive this one equals tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. Okay, alright, so up to now we have derived tangent alpha beta equals this combination of tangent alpha, tangent beta. So if I write out, this one equals tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. This is the sum formula for tangent. Now, of course, you will consider difference if alpha minus beta, right? If you alpha minus beta, all you need to do is to change beta to negative beta, and because tangent function, we know it's an odd function, so tangent negative beta is negative tangent beta. But from here, we can derive the difference function, the difference formula. So tangent alpha minus beta, this equals tangent alpha minus tangent beta, and here's 1 plus tangent alpha times tangent beta. We just use, so from here to here, we can just use as I said, we just use the property, tangent function is odd function. We just use tangent negative beta is negative tangent beta. Besides sine, cosine, tangent and cotangent, there are two more trigonometric functions called secant and cosecant. Secant x is defined as the reciprocal of cosine x, so that's 1 over cosine x. So this function is well defined as long as cosine x is not 0. Because cosine function is 2 pi periodic and even, therefore this function is also 2 pi periodic and even. The other one is called cosecant. Cosecant x is defined as the reciprocal of sine x is 1 over sine x. Since sine x is odd function and also 2 pi periodic, therefore this cosecant function is also 2 pi periodic and is odd function. Now let's see two trigonometric identities associated with secant and cosecant. First, let's look at secant. If we have 1 plus tangent x squared, this equals, by definition, tangent x is sine x or cosine x, so this is sine x squared over cosine x squared. Okay, this one can be, if you combine this into one fraction, we'll get cosine x squared and cosine x squared plus sine x squared. Okay, for cosine x squared plus sine x squared, this one equals 1. Therefore, we get is 1 over cosine x squared, but 1 over cosine equals secant. Therefore, this one equals secant x squared, and we derive a trigonometric identity. 1 plus tangent x squared equals secant x squared. Similarly, we can also derive 1 plus cotangent x squared equals 1 over sine x squared, that is cosecant x squared. Okay, so these are two trigonometric identities associated with secant and cosecant. So far, we have 4 trigonometric functions: sine, cosine, tangent, cotangent, secant, and cosecant. Now, let's compare the range of their values. The range of values. For sine and cosine, two most basic ones, we know their values. So first of all, sine and cosine are defined for all real numbers x, and the collection of all possible values is between -1 and 1. This is 2, -1, and 1. Now for tangent and cotangent, tangent x by definition is sine x over cosine x. Cotangent x by definition is cosine x over sine x. Okay, so tangent x and cotangent x, they are pi periodic. The least period is pi. Cotangent is, both of them are odd functions. Tangent is defined when cosine x is not 0. Cotangent x is well defined when sine x is not 0. Now, if you look at the collection of the possible values, the range of tangent and cotangent, if we remember the graph of tangent and the cotangent, the collection of the values is from plus infinity, negative infinity, all the way to plus infinity. Okay, so the collection of possible values is from negative infinity to plus infinity. So from negative infinity to plus infinity, or we say is the collection of all real numbers. Okay, now for secant and cosecant, secant x is 1 over cosine x, cosecant x is 1 over sine x. Now, these two functions, they are also 2 pi periodic. 2 pi is their least period. This is odd function, this is even function, this is odd function. Now, because cosine is between -1 and 1, therefore it's reciprocal, it's always either is no less than 1 or is less or equal to -1. Similarly, for cosecant x, therefore the range of values is bigger or equal to 1 or is less or equal to -1. Next, let's look at several problems that are related to tangent and cotangent functions. Example 1. This is past the AMC12 question. The problem says, if we look at this trigonometric equation, tangent to x equals cosine x over 2, how many solutions does it have on the interval 0 to 2 pi? Now, as we mentioned before, if we need to solve trigonometric equations, there are usually 2 ways. The first one is algebra method. We solve the equation by using various trigonometric identities. The second method is topological, or we say geometric method. Now, for this one, because it involves both tangent and cosine, double angle, half angle, if we try to use trigonometric identity to solve this one, it's kind of complicated. This problem only asks for the number of solutions instead of what they are. For this one, the more convenient way is to use the topological method. Well, topological method just means we draw the graph of this function, tangent to x, and the graph of cosine x over 2, and just count how many intersections they have. Okay, so let's draw the graph, tangent to x and cosine x over 2. So we use the topological method. I would say geometric method. All right. Let's recall, this is the graph for cosine x, which is 2 pi periodic, and this is the graph for tangent x, that is pi periodic. Then, if you look at the tangent, if you go from tangent x to tangent 2x, what you do is you compress the graph. In particular, the period of tangent 2 pi x, this one becomes, this is pi over 2 periodic. Right? Okay, if you use the 2x. Now, if you go from the cosine x to cosine x over 2, what you need to do is you need to stress the graph of cosine x. Therefore, this one is a 4 pi periodic, the function of cosine x over 2. Now let's draw the graph of cosine x over 2 and the graph of tangent to x. Okay. So here is from 0 all the way to 2 pi. Here we have this is pi and pi over 2. And this is 3 pi over 2. Now, let's first draw the cosine x over 2. So cosine x over 2 start from 1. And it equals 0 at pi. And then it goes to right here, which is becomes -1 right here. So this is the graph of cosine x over 2. We say put y equals x over 2. All right. Now let's draw the graph of tangent to x. So as we said, for tangent to x, it's what we do is we compress the graph of tangent x. The period becomes pi over 2. So we draw. So first, let's draw those asymptotes. Here is we have the asymptote becomes pi over 4 because the period. This is the period becomes pi over 2. So that's what we have. Right? Okay. Here is pi over 4. This is 3 pi over 4. And here's negative pi over 4. Okay. Now let's draw the graph. The graph within this period, we have those vertical lines are asymptotes for tangent to x. So this is what we have. And then within this period, this is what we have. And here we have and then we have and also we have one more. focus on the interval is we focus on from 0 to 2 pi, so it's all from 0 all the way to 2 pi. So that's the place we focus on, from 0 to 2 pi. Then we can count the number of intersections. Okay, so the first intersection here, so this is number 1. The first intersection is 1. And then the second intersection is right here. So this is the second intersection. The third intersection is the pi, so it's right here. So this is the third one. And then we have the fourth intersection here. So this is number 4 intersection. And then we have the fifth intersection is right here. This is the fifth intersection. Okay, so the point is now from the picture it's clear. In total it has 5 intersections, which is equal to saying this trigonometric equation has 5 solutions. Example 2. This is past the AMC problem. The question says, if I know tangent x plus tangent y equal 25, cotangent x plus cotangent y is 30, then what is tangent x plus y? Now obviously, here we can use the sum formula for tangent function solution. If we recall the sum formula, so tangent x plus y equals tangent x plus tangent y. So here's 1 minus tangent x times tangent y. Okay, now we already know tangent x plus tangent y. So this one is given, which is 25. Therefore, in order to get tangent x plus y, we need to figure out this missing piece is tangent x times tangent y. Okay. How we figure out tangent x times tangent y? We can use another piece of information, that's cotangent x plus cotangent y. So let's see how we use this piece of information. Cotangent x plus cotangent y. Well, cotangent x is just the reciprocal of tangent x. So this is 1 over tangent x plus 1 over tangent y. Okay, let's combine these two fractions into one. Use the common denominator. That's tangent x times tangent y. Here's tangent y plus tangent x. Okay, all right. We know this add together equals 30. And again, we have tangent y times tangent x. This is given is 25, so this one is 25. From here, we immediately derive, okay, so 25 divided by tangent x times tangent y is 30. From here, we immediately derive tangent x times tangent y equals 25 over 30, which is 5 over 6. And then, okay, so we get this missing piece. We can plug this one back into the sum formula. Okay, so we get is 25, 1 minus 5 over 6, and that's 1 over 6. So eventually we get 150. Example 3. This is a past AMC problem. What we need to do is to find the smallest positive integer solution x to this trigonometric equation. Now, the left-hand side is tangent x, the right-hand side is cosine 96, sine 96, and cosine 96 minus sine 96. Clearly, what we need to do, because the left-hand side is tangent, the right-hand side is cosine and sine, what we need to do is to convert this into things that are expressed in terms of tangent instead of just sine and cosine. There are multiple ways to convert this into things just involves tangent. The most convenient method is to, let's say, okay, clearly, because here I have cosine, sine, right? If I divide cosine on both sides, then I'll just get on the above, on the bottom, then I'll get a tangent, right? Okay, solution. So as I said, the idea is I will try different ways to convert this into something that only involves tangent. Okay, so we have the tangent cosine 96 plus sine 96 over cosine 96 minus sine 96. we divide cosine 96 on the above and on the bottom, right? And this leads to equals this one cosine cancel, that's 1. And here what we have is sine 96 divided by cosine 96. And then we have is 1 minus sine 96 over cosine 96. Okay, now sine divided by cosine by definition is a tangent. And this is 1 plus the tangent 96 and 1 minus tangent 96. Alright, what's next? We want to write this, the goal is to write this as a tangent of angle x. When we look at this, we say, wait a second, this is kind of like the sum formula for tangent function, right? Let's recall the sum formula. The sum formula for tangent function says tangent alpha plus beta equals, this is tangent alpha plus tangent beta, and 1 minus tangent alpha times tangent beta. Now if you compare the sum formula of tangent function with the expression here, you see we already have 1 here, 1 minus, it's very similar. But the only thing is, here we have tangent alpha, this is tangent 96, but we have 1 here, right? Then we just ask ourselves, okay, can I write 1 as a tangent something? The answer is yes, that's tangent 45, right? Okay, so here's the key point. So now we say, alright, so this one just equals tangent 45. And here is, okay, tangent 45 is 1, and this is just multiplied by tangent 45. Alright, by that, by replace 1 by tangent 45 here and there, we can write this as the sum formula of tangent function. This one equals, what do we have? This is just tangent 45 plus tangent 96 and 1 minus tangent 45 times tangent 96. Alright, so this is perfect match for the sum formula, okay? And then we just get this one is tangent 45 plus 96, which is tangent 141 degree. Now we want this equals tangent x. Of course, because there are infinitely many x that satisfy tangent x equals tangent 141 because tangent function is pi periodic. But here we are looking for is the smallest part in the solution to this. Therefore, we conclude x, the smallest one is x equals 141. So here, the key, if we review the solution, the key is to realize this one is a special form of the sum formula when one of the angle is 45 degrees.